So we are discussing about the topic of square roots and cube roots. So we are going to find the square roots and the cube roots using various different methods in this topic. But before that, we will try to know what are square numbers and cube numbers. So these are the different types of numbers we need to identify before we actually go to finding the square root. So let's start with perfect squares and square numbers as the initial topic, contents of the topic what we're discussing for today. So if I can express any rational number as a square of a rational number expressed as a square of another rational number, then that rational number is called a perfect square. A rational number which can be expressed as square of another rational number is called a perfect square. So a perfect square is a rational number which can be expressed as a square of another rational number. So let's see with an example what numbers form a square number, perfect squares, and what numbers do not form perfect squares. For example, I have 4. I can write this as 2 square. So 4 is a perfect square. Next, 9. I can write as 3 square. So 9 is a perfect square. I have 16. I can write this as 4 square. So 16 is a perfect square. I have 1.44, which I can write it as 1.2 whole square, because 12 times 12 is 144. So 1.44, which is a decimal or a rational number, can be expressed as 1.2 whole square. So 1.44 is called a perfect square. So these are the various examples of perfect squares where the definition clearly says that a rational number which can be expressed as a square of another rational number. So all these are rational numbers which are expressed as squares of the other rational numbers existing in the number system. So this is the definition of a perfect square. Next, if I have the next definition here is the square numbers. Now the square numbers are defined with the same definition, but instead of rational, I have an integer. So the definition says an integer. In the previous case, it was a rational number, but here it is an integer. And we have discussed integers and rational numbers in the previous session when we were discussing about the number system. So an integer which can be expressed as square of another integer is called a square number. So this is how we define the square number, where an integer which can be expressed as square of another integer is called a square number. So let's see some examples for square numbers. So an integer which can be expressed as square of another integer is called a square number. For example, if I take 4, this can be written as 2 square. Therefore 4 is a square number. 4 is also a perfect square, but it's also a square number because 4 is an integer and square of that, which is 2, is also an integer. And then I take 16, which is 4 square. So 16 also is a square number. If I take 289, which is nothing but 17 square, then 289 is also a square number. It is also a perfect square. But if I take which is square of this, is not a square number because this is not an integer. not a square number, since 0.01 does not belong to Z. So this does not belong to set of integers. Therefore, this property does not make this a square number, but this is a perfect square. Next, if I have, say, for example, I have 7, I can express 7 as square of another number. Say this can be written as root 7 into root 7, which is 7. Therefore, this can be written as root 7 whole square. But since 7 is root 7 whole square, is neither a square number nor a perfect square, because root 7 is not a square number and is not a perfect square. Since the rule says that it should be either a rational number for being a perfect square, it should be an integer for being a square number. Root 7 is neither an integer nor a rational number, it is an irrational number. Therefore, since root 7 does not belong to Z and root 7 does not belong to Q, therefore it satisfies this leads to not being a square number, this leads to not being a perfect square. So these kind of numbers which can be expressed as square of the roots cannot be a perfect square or a square number. These kind of examples do not include in either of the square numbers or the perfect squares. So when we have seen the two basic definitions of the square numbers and perfect squares, we should be able to differentiate the main difference which stands between this and this. For perfect squares, the numbers considered must be rational, and for square numbers, the numbers considered must be only integers. So the question is about finding all square numbers between 1 and 100. So square numbers, let's start with 2 square, which is 4. Next, the next square number is 3 square, which is 9. 4 square is 16. 5 square, 25. 6 square, 36. 7 square, 49. 8 square, 64. 9 square, 81. And 10 square is 100. But I don't take this because I want all square numbers between 1 and 100 exclusive. I don't include 1 and 100. So the square numbers here are identified to be the 4, 9, 16, 25, 36, 49, 64, 81 and 100. So these are the square numbers which are identified in case of the values between 1 and 100. So the square numbers between 1 and 100 are totally 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 square numbers between 1 and 100 is how I identify in case of this example problem. Now let's take the other example which says how many perfect squares lie between 1 and 100. Now going with a similar example as in the previous case where we have found the square numbers lying between 1 and 100, finding of perfect squares between 1 and 100 would not be that easy, because square numbers or the square of integers, there are limited number of integers between 1 and 100, but perfect squares or the squares of rational numbers, there are unlimited number of rational numbers between 1 and 100. So square of any rational number would give me the other rational number lying between this. So it is very difficult to identify rational numbers which can be squared between this. So the answer for this would be infinitely many perfect squares lie between 1 and 100. So the reason being that infinitely many rational numbers lie between 1 and 100. So answer is infinitely many perfect squares lie between 1 and 100. The reason being that since there exists infinitely many rational numbers between 1 and 100. This being the reason you have infinitely many perfect squares between 1 and 100, but you have limited number of square numbers between 1 and 100. The list being 1, 2, 3, 4, 5, 6, 7, 8. So 8 square numbers lie between 1 and 100, but here you have infinitely many perfect squares. So that is how we understand this. Now, the next topic which we are going to shift to here is, the next content out here is finding the units place of a square number. Now we have understood the square numbers through the definition as we have seen in the previous session. Now we are going to find how the units place can be identified in a square number. Now let's find the units place of a square number. Now what is the units place? So let's recap about what is a units place. Suppose I take an example problem 553, then in this case my position in the last digit is called the units place. Then this shifting to the next digit is the tens place, then hundreds place, 10,000, so 1 lakh. So it goes on, but the last digit will identify the units place of the given number. So that is how we identify the units place. So in this case, this is the units place. Now, in this problem, I wanted to identify the units place of this whole problem, of this whole square number. This is a square number because 553 is an integer. Now I wanted to find the units place of this square number. So when you want to find the units place, we have to just identify the last units place of the given number and then square it individually. Not the whole number which is squared, but only the last digit which needs to be squared. So units place of the square number this will be nothing but square of this, which gives me 9. So this will be the units place for the square 553 raised to power 2. So this is how I identify the units place. So let's take one more example. I want to find the units place of this square number. So I identify the units place of this. So therefore 9 being the units place of the number inside the square. So units place of 999 whole square would be the square of this, and the square of the last digit is nothing but 81. Therefore the last digit of this will give me the units place. So the last digit would give me the units place. So like this, we can find units place of any big number by just taking the last digit and just squaring it. So units place is quite easy because you need not square the whole number, where the simplification becomes more complex and more lengthier. The only concept is we take the last digit, however big the number is, and then we just try to find the square of the number, which the units place gives me the last digit of the square of that particular last digit number. Now let's take an example where I'm going to connect the units place into deciding whether the given square number is an even number or an odd number. So in case of this, I've taken a very large number as a square number because however big the number is in its square form, you can just find its justification of an even or odd number in 2 or 3 simple steps. It is only about finding its units place, and then the units place will decide whether the given number is an even number or an odd number. So in case of this example, I have taken the problem 395468972197 whole square. So for this square number, I want to decide whether it's an even or an odd number. It's very simple. So I'm going to just take the units place. Now in the units place, I have 7, that is the last digit, which is 7 inside the square. So in this base number, 7 square will give me 49. Therefore the last digit of the entire number would be the last digit of this, which is 9, in its units place. So since 9 is an odd number, as we know that the odd numbers are 1, 3, 5, 7, 9 and the even numbers are 2, 4, 6, 8, 0. So therefore 9 is an odd number. Indirectly, the whole of the square number becomes an odd number, and an answer which is obtained in 2 or 3 simple steps. So for any number, you can just justify the even or odd concept by just picking its last digit, squaring it, and the last digit will decide for that squared number, will decide the justification of the entire problem being an even or an odd number. Next, continuing from here, I have the next concept is I want to find the number of integers which lie between two consecutive squares. So let me take two square numbers and I wanted to find, when I take the two consecutive squares, I want to find how many integers lie between them. So let's take with 1 or 2 examples to understand this concept more clearly. So for example, I have in this case, let me take the consecutive integers 1 square which is 1 and 2 square which is 4. So in this case, I identify that the consecutive integers between 1 and 4 when you simplify are 2 and 3. So that implies the number is 2. Therefore, there are 2 consecutive integers between 1 square and 2 square which are 2 and 3. The number is 2. So indirectly this is obtained by taking the number as twice the base number, which is nothing but twice of the base number. The base number of the first consecutive integer, which is nothing but twice the first base number, which is nothing but 1. The base number is the value inside the square, which is 1. So 2 times of 1 is 2, which very much tallies with this. So let's see if this holds true for every other number. So let me take in the second case the consecutive integers as 2 and 3, so that the squares of 2 and 3 are 2 square and 3 square with 4 and 9. So in this case, let's see how many integers lie between 4 and 9. 5, 6, 7 and 8. So here I find that there are 4 consecutive integers which lie between 2 square and 3 square. 1, 2, 3, 4. So here I find that the number is 4. But let me just verify with this formula. Here is the formula. So let me use the formula. Twice of first base number should give me the value as 4. So here in this case, twice of the first base number in this case is 2, and the first base number in this case is 1. So twice of 2 is 4, which is very much tallying with the given obtained value from counting the numbers. So we observe that there is a pattern where whenever I get the number of integers lying between two consecutive squares, I get the number to be exactly twice of the first base number. So this is a formula or a pattern which is continued for any number of consecutive squares. The formula says the number of integers lying between two consecutive squares is twice the first base number. So let me try with a bigger problem. Let me take the bigger problem. Six square is 36 and 7 square is 49. So these are the consecutive integers where the first base number is 6. So let me just verify this with the formula and then randomly with counting of the numbers. So when I clearly see the numbers lying between 36 and 49 are 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47 and 48. So if I count the number of integers which lie between 36 and 39, I find that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So totally I find that there are 12 such integers which lie between 36 and 49. When substituted through the formula, this is nothing but 2 times of 6, which is nothing but twice of first base number, exactly the first base number, which is 6. So this is true for any number of consecutive integers which are taken into consideration. So this formula helps me in identifying the number of integers between two consecutive squares when the square numbers are very large numbers. If the numbers are very huge, then in that case I can use directly with the formula and then identify the number of integers which lie between the two consecutive square numbers.